This lesson is all about sets. Sets are collections of objects, items, products, etc. If you don't have any of those items in your set or collection, it's called an empty set. Now, that is notated by a circle with a cross through it or an empty set of brackets. Do not combine the symbols, because if you write a set composed of an empty set in it, it's no longer empty, technically speaking. So either or is fine. If you do have items in your set, you can use set notation. So you have squiggly brackets and commas to separate the objects. For example, if you're collecting coins, you could say you have a set of pennies, dimes, quarters. For example, if you had an infinite set, so say the set of even numbers, you could write 2, 4, 6, and since there's a pattern, you can write ... and that says continue the pattern. Each of the items in the set are called elements or members of the set. So there's some notation associated with this. If an item is an element of a given set, this is basically a language that you're learning, you could say that 2 is an element of the set of even numbers. However, you would say that 3 is not an element of the set of even numbers. Now, if you want to look at subsets, it's an entire set that is composed of some of the elements of the given set. It has to be contained exactly within. So in this picture, A is completely contained within B. Therefore, A is a subset of B. So here's some notation. A is a subset of B, is notated in this way. And A is not a subset of B, is notated the same but with a cross. So let's make an example of that. For even numbers, you could say that 2, 4 is a subset, completely contained within all the even numbers. However, say you had a set of 2, 3, since 3 is not an element of the set, therefore 2, 3 is not a subset of 2, 4, 6, etc., the even numbers. So what can we do with these sets? Well, we have 3 options. One relates to adding them, one relates to multiplying them, and one relates to subtracting them. So in the world of sets, we're going to be using Venn diagrams. I think sometimes when you see a Venn diagram, it's a little easier to visualize the set. So let's take an example here. Let's say A is equal to the set containing 2, 3, and 4. And B is the set containing 3, 5, and 6. I've purposely chosen the sets to contain one common number, and that's 3. So if we write that in here within this bubble, everything in A has to be within this red bubble here. So the 3 is in the common part of A and B. The 2 and the 4 are out. The B is 5 and 6 and 3. So if you take the union and think of holding your hands up, it makes a U. You're unifying or taking the sum of your 2 sets, which basically translates to, hey, everybody is welcome. So A union B, unifying A and B, saying that 2, 3, 4, 5, and 6 are all welcome. Order does not matter with writing these sets, and also you do not have to repeat the common number twice, you just leave it once. All right, next up is the product or the intersection. Here it's the more elite a distinction because you want to intersect, cut off everybody that's not common and only allow the people who are in both parties, or the numbers in this case. So here you've got A intersect B. Think of a cookie cutter. You're cutting out just the common part between A and B, which in our case was just a 3. You don't always have to draw a picture like this, but I think for the purposes of just the basic understanding of intersection, it's a little easier to see it on a picture. So the only thing in common between A and B is 3, and that's it. Sometimes there's nothing in common, and that gives you a disjoint set. So if your intersection is empty, so if you had A and B and they didn't intersect at all, then you would have disjoint sets. Now you also have the difference, so everything in A but not B. So everything in A was 2, 3, and 4. 3 was common to B. So because you want not anything in B, you're basically throwing out anything that was in B, leaving us with just the 2 and the 4. Great. Sometimes you also have a universal set, a set denoting all the possibilities in your collection. So in our case, we usually use the real numbers because the real numbers are all the numbers we know of. And then within those numbers, we could pick sets containing certain numbers. If you were talking about coins, the universal set would be all the possible coins in the world. And then from there, you'd be including pennies, dimes, quarters, etc. So it's usually drawn as the box in a Venn diagram is basically the world of objects that you have available to you. The complement of a set. The complement is basically everything that's in the universal set that does not belong to the set you're taking the complement of. So in a Venn diagram, it would look like this. You have all your possibilities. So let's say all real numbers in the world, all the possible numbers existing. And then you have some set A. Well, actually, let's simplify this so that we are able to maybe visualize it. So let's say our universe only consists of 1 through 5. So the numbers 1 through 5 could be our universe in this case. So let's say we had a 1, 2, 3, and then 4 and 5 were in A. So A equals 4 and 5. Universe equals 1, 2, 3, 4, 5. So therefore, A prime in this case would be everything that is not in your A. It's everything that's outside of it, which in this case is everything except for 4 and 5, which is 1, 2, and 3. So let's take a look at some more examples here. You can see in number 1, you have a lot of double-braced letters that you might not know the meaning of. So let's first define those to start off with so you know what they mean. So the double-braced n is basically the set of natural numbers. Natural numbers are what you start off learning when you first start learning numbers, 1, 2, 3, etc., all the way up. Whole numbers is the next stage in learning numbers. Think O for 0. So it's when you realize that there is the possibility of having nothing. You move up to whole numbers, and that's basically including 0, 1, 2, 3, and up. Kind of reflects the history of mathematics. 0 was not known or recorded for a long time after 1 was recorded. Then this funny Z here, I know it's kind of weird, it stands for integers. So that's the only one that doesn't really reflect the name of it. But Z stands for all the integers, which is basically your entire number line. So -3, -2, -1, 0, 1, 2, 3, and so on. Forever and ever. So, and then we already talked about real numbers. The double-braced R are real numbers. So sometimes mathematicians use these shortened letters here to represent those, so it's good to just have an understanding of that. Okay, let's take a look at these examples. So in the first question, they're asking us to place one of these signs to make each of the following statements true. The first two relate to being elements of, so your first component needs to be an element, and the next ones can pertain to being subsets. So the first part needs to be a set. We didn't actually really go over that, so don't worry about that one. We either have subset or not a subset. So in the first problem, you have a set of 1, 2, and 3. So you cannot use the element symbols. You need to use the subset symbols. So we're checking, is this set a subset of the natural numbers? So is 1, 2, 3 contained in 1, 2, 3 and on? Well, yes, it is. So therefore, it is a subset. It is contained within the natural numbers. The next one, you've got 4, 2, and 2, 4. Now these are exactly the same set. You've got the same items in each bag. They're exactly the same. So this example actually is a subset, but it's also this symbol that I erased. It's a proper subset also. So if you just put subset, that's fine. If you would like to be special, you can say proper subset. It's basically like saying they're equivalent sets. We didn't introduce it earlier, but there it is. Okay, and the next one, you've got this thing, which if you recall from the first page, this is called the empty set. So the empty set is still a set, so you need to use the subsets. So is the empty set contained within the integers is the question. So is a set of nothing in it, can that be part of the set of basically your number line? Well, of course. If you think about it, an empty set can be a subset of any set. You can always have nothing contained within a whole bunch of other things. Alright, the next one, this now is a 0, and therefore it's an element. So they're asking, is 0 an element of the integers? And in the integers, yes it is. Therefore it is an element. Here we've got the integers, which is a set, and the whole numbers, which is a set. And they're asking, is the set of integers, that means all the negative 0 and up, contained within the whole numbers, 0 and up? Well, actually, I think it's the other way around, because 0 and up is contained within the number line. So in this case, it is not a subset that way. However, it is the other way. All right, and last one here, 0, the element, has no set brackets, is it part of n, the natural numbers? Well, in the natural numbers, they didn't know about 0, so it is not an element of the natural numbers. So that's how you use those symbols. Now, let's do some operations with these sets. So A is 1, 2, 3, 4, 5, B is 2, 4, 6, C is 5, and 7. They want us to find the intersection, think N for intersection of A and B. So look at A and look at B and look for common components. What common numbers do you see? Well, we see a 2 and a 4, and that's about it. All right, let's take the union, U for union of A and B. That means everybody's welcome. So let's take everybody who is in A and B and don't repeat anyone. So 1, 2, 3, 4, 5, and 2 and 4 were already mentioned, and 6. So basically, like, you've got subcommittees and committees. There's people who are part of everything and they want to be in the soccer team and the football team. So they're part of everything. So that's like, in this case, the 2 and the 4, they're part of both teams. However, the rest of these people here are only part of A, and the rest of this is only part of B. All right, now let's take a look at A not including B. So only those who are in A and not in B. So who is in A, not in B? 1, 3, and 5. And if you really like, you can draw this out and draw out an A and B and write it out so that you see that 2 and 4 are stuck in the middle and 6 is left over, 1, 3, and 5 are left over. Sometimes that's helpful. Now we want to look at the intersection of A and C. So only the common components, cookie cutter, common components of A and C. So we've got 5, and that's about it. Cookie cutter between B and C. So common things, common elements between B and C. Now, okay, 2, 4, 6, 5, and 7. Is there anything common? No, there's not. So the intersection is an empty set. So you could write either empty brackets or you could write a 0 with a slash through it. Now, this is where the party is at because everyone is welcome. Whoever's in A, whoever's in B, whoever's in C. Everyone's welcome. So what numbers have been used? 1, 2, 3, 4, 5. And you can write them in any order. It really doesn't matter. I'm looking at increasing order just because. So 2 and 4, 6, 5's been said, and up to 7. All of those numbers have been mentioned in A, B, and C. Alright, you could also be asked to give an example of disjoint sets. And sometimes you need to illustrate a Venn diagram, which is the bubbles that you've seen earlier. So disjoint sets, you could say 2 sets. So let's say A is 1, 2, 3, B is 4, 5, 6. Done. There's your Venn diagram. You've got 2 bubbles. There's the universe. Could be the real numbers, whatever. A and B are disjoint. There's nothing in common. And shading, let's take a look at some shading. So let's say you have the universe, A and B, and then you want the complement of A union B. So let's first find what A union B is. A union B would be everything in A, everything in B. That's A union B. Now let's take another color, and everything that's not part of that. Let's see here. Is everything outside of that. So sometimes you have to find the first part to find the complement after. So the blue part is the complement.